What are you going to do now?
This is a tensile test, and so we're going to pull this sample to breaking. You can see there's our weld right there that we're testing right now. And so we're going to pull this sample, see where it fails, and measure the force required to cause the failure.
How are you going to do that? What machine are you going to use?
We're using the tensile frame right here. To do so, we need to...
How you record the data?
Data is recorded on one of the most important graphs that an engineer can make, the stress-strain curve. So we have the load on the one axis, saying how much we're actually how much force we're putting on there, and then the extension, how stretched out this piece is getting. And you can see that the more force we're putting on it, the more stretched out it becomes, until it eventually hits a maximum, which is about where we're hitting right now. So we got the strength and the break location. Those are two important things. The last thing we need to get is the final elongation.
So what is this machine, Stephen?
This is a hardness tester. So besides the tensile test and the sharpie test, the hardness test is the third big test that a materials engineer needs to use. And it's going to test the hardness of our material, how easily it resists indentation in this way. Once that's all done, we can see the big indent that was made in our sample.
Can you show us where is it?
Right there. And so what we would do is measure the size of that indent.
How do you measure that?
A large indent means that it's softer, a smaller indent would mean that it's harder. And for this particular test, we measure the indent using a handheld microscope.
So that's a microscope, right?
Yes, and then we can look through here to get a very precise measurement on the size of that indent, which will then tell us the hardness. These are additional types of hardness tests. There's a variety of different ways that we can do hardness testing, but they do tend to be more or less the same. These here are all known as Rockwell hardness testers. This is the Vickers hardness tester. Yeah. And so it's good for doing micro hardness measurements. It's capable of testing a very, very small region of the weld or of the heat affected zone around the weld to get some more precise detail on exactly what's happening.
Yeah, Stephen.
This is our Sharpie tester. A Sharpie test is done to measure the toughness of a material, which is kind of another way of saying the resistance to cracking. We are going to measure the energy that's absorbed by the sample as it fails. And so the way that works is we lift up this big hammer. It has a lot of energy right now. Put the sample down there and swing this to break it, which you'll see in a moment.
And what temperatures do you measure this impact?
Temperature does have a big effect on that resistance to cracking. The colder the sample is, typically the less well it performs. And so we also have our chillers here in order to cool down our samples, sometimes as low as minus 60 degrees Celsius, to test the effect of temperature on our cracking resistance for our materials. Very, very important for things like pipeline applications. We also occasionally use the furnaces in order to test at higher temperature, which for steel, it tends to give a higher toughness as well.
So what are you doing now?
This is a weld sample that one of my students prepared. You can see the small little weld there, just connecting two small plates. So this is two samples in one. We're just going to put it onto the microscope to take a look at the microstructure of that weld and see what exactly is going on there. So this is a zoomed in view of the weld, fairly zoomed out for the microscope. It's only 5 times magnification. So this is a zoomed in view of the weld metal, about 5 times magnification. This is actually the most zoomed out that the microscope can do. And this right here is the weld metal, and with the zoomed in view on the microscope, you can see these individual grains That's what actually makes up a metal, which we can actually see on the microscope there. And if we move across here, we get into the heat affected zone. That's the heated area next to the weld where the grains changed, and then the parent material over here, which was unaffected by the weld. As you can see here as well, the two plates that were joined up, they carry on back by the weld metal here that connects the two of them now. Here is our collection of failure samples with a few more in the other cabinet as well. Just to show you that we have many different failures that we've looked at, one of the main topics in our program, and lots of hands-on examples to show you various things, such as pitting, that you can see in this pipe sample. This is a type of corrosion that occurs on steels. We also have many non-metal failure samples as well, since we do talk about that in a few courses too.